In this video, we are going to learn how to divide fractions using a common denominator. So the algorithm that I'm going to show you in this video is what we like to call a bridging algorithm. And basically a bridging algorithm just means that it's something that you use to bridge a visual model to the most efficient or abstract model, or the most advanced model or algorithm for solving. So you may actually already know the most efficient shortcut to divide fractions, but I'm willing to bet that you probably don't know why it works. So this algorithm here is going to help us bridge our understanding of the visual model to solve, and then how to do it in the most efficient way. Okay, so dividing fractions using a common denominator. Okay, so here's the procedure. You are going to use the least common multiple, or the LCM, to find a common denominator. And all you do, once you've done that, is you divide across and simplify. So it actually looks a lot more like multiplying fractions than it does look like dividing fractions with the methods that you may have already been shown. Okay, so step one. Okay, so we're going to start with our original division problem. Okay, so there's an original division problem, and we have 3/4 divided by 1/3. Okay, so our next step is going to be then to find the common denominator. Find common denominator. Okay, so I can see we have fourths and thirds, and they tell us that we need to use the LCM, the least common multiple. So if I'm skip counting by fours and I'm skip counting by threes, when is the first time I land on the same number? And we know from our multiplication patterns, we know that that's going to be 12. So I'm going to convert both of these fractions to their equivalent form in twelfths. Okay, so 4 is getting converted to twelfths, and so I'm making this, or I'm increasing this by a scale factor of 3. So my 3/4, I'm going to multiply my denominator by 3. That gives me the 12, and then I multiply my numerator times 3, and that gives me 9. Okay, I'm going to go through the same process over here. If I'm converting it to twelfths, 3 times 4 is going to give me 12, and so I'm increasing this fraction by a scale factor of 4. So 1 times 4, is going to be 4. Okay, and then my next step, now that I have my equivalent expression, my next step is going to be to divide across. And I know what you're thinking. Divide across? You never divide across. Actually, you can. You probably have just never seen it before, or the people that have shown you previously, they probably just didn't know that. So dividing across, I'm going to take my numerators, 9 divided by 4, and that's going to stay all over my denominators, 12 divided by 12. So there they go. I'm just going across for my numerators and my denominators. Okay, so my next step is then to simplify. Okay, so I now have 9 divided by 4, and I'm just going to leave that there for now. So 9 divided by 4. I'm going to simplify this denominator. So 12 divided by 12. We know that anything divided by itself is going to equal 1. So I'm going to take that fraction and put it all over 1. Aha, now I see something interesting. I now have something over 1, and we know that anything over 1 in a fractional value, if your denominator is 1, you know that it's equivalent to just whatever the numerator is. So 9 divided by 4 all over 1 is the same thing as 9 divided by 4, which if we put that back into fractional form, 9 divided by 4 looks like 9 over 4, right? So because we know a fraction is just another way to write division. Okay, and now the last step. Now that we have this improper fraction, we are going to convert it to a mixed number, if you need to. I mean, sometimes it won't be in that form, but convert to mixed number. Okay, so I'm going to see how many times does 4 go into 9. It goes 2 times with 1 left over. That's going to be my numerator. And then I'm going to leave my denominator the same. There's my fourths. So you'll remember from our using area models, you'll remember that we split our squares up into 12ths, right? Because we had the thirds going this way. We had then the fourths, or excuse me, we had the fourths here and we had the thirds there. And then we broke them up into the same number of pieces and we had 12ths, which was the common denominator, which is what we did here. So it's the same process, but now without the visual model. All right, now, okay, so how is this a bridging algorithm? Well, this is completely and 100% connected to the algorithm that you know, also known as keep, change, flip, or multiply by the reciprocal using the correct mathematical vocabulary. So I'd like you to write here, this is really important. When you do that, when you multiply by that reciprocal, you are taking a mathematical shortcut. And you are going all the way from step 1 and you are skipping down to the end of step 4. It is a mathematical shortcut. And I'm going to write here, multiply by the reciprocal. Multiply by the reciprocal, which is also the same as keep, change, flip, which I don't particularly like keep, change, flip, but I know that's what you probably heard of before, so we'll just leave it there. Okay, so what is it that we're doing? So when we multiply that reciprocal, notice how you end up with 9/4. If I go back to my original problem, where am I getting that 9? Well, you can see if you take your numerator of your first and you multiply it by your denominator of your second fraction, you get 9. If you take your denominator of your first fraction and the numerator of your second fraction, 4 times 1, you get 4. So it looks like this, 3/4. And you can change that division to multiplication and then find the reciprocal. So that 1/3 becomes 3/1. And that equals 9/4. So that multiply by the reciprocal or keep, change, flip algorithm that you know is just a mathematical shortcut to bring you all the way from step 1 to the end of step 4.